Well, this morning I thought we would go through some rather elementary definitions and discussions, and part of which would be preliminary to getting a perspective on the course, as well as a little preparation for better understanding of the laboratory period. Now, first of all, I've made a little brief outline here of a not official definition, but a kind of a definition of the brandy or distillate types as in accordance with their use in the wine industry. Fundamentally, there's two types produced, as far as purpose is concerned. The first is a beverage brandy, or beverage brandy distillate. Strictly speaking, we speak of a beverage brandy distillate as a material that's produced directly from the distilling equipment by distilling wine, and the characteristics of this legally is that the maximum proof of distillation is 170. This is a rather simplified definition, and the legal definitions or standards of identity for brandy are rather complicated, and you arrive at this by eliminating the things that cannot be, rather than a straightforward definition. But in effect, brandy that is intended to be aged in wood and eventually sold for sale as a direct product, or in other words, as beverage brandy, is generally made or has to be made out of distilling material that is equivalent to the whole grape. That is a standard wine. Cannot be residue material. Otherwise, it would incur the appellation of residue brandy. So beverage brandy is made from wine, or essentially the whole part of the grape. And the other essential limitation is that it has to be distilled at 170 proof or less. The purpose of that, ostensibly, is to ensure that it has flavor components retained in the distillate. Strictly speaking, it's not proper to call the distillate when it comes out of the still, which is colorless, of course, as beverage brandy, because it doesn't really become beverage brandy without qualifying terms until it has been aged in wood for at least 2 years and then bottled. We're getting into a few side points here which do refer to the legal aspects. For example, the law requires that beverage brandy be aged at least 2 years in barrels or in wood. And if it's not, it's called immature brandy. So, strictly speaking, then we speak of beverage brandy distillate. And secondly, we have what we can lump together called wine spirits, that which is produced and used for the production of dessert or aperitif wines, or a term that's not maybe in such good favor in the wine industry, fortified wines. The wine industry and the Wine Institute prefers we don't use the word fortification and fortified wines because the connotation is bad. But that's the easiest thing to say. The alternative term to fortification of wine is the addition of wine spirits, or wine spirits addition. So now, instead of going through the process of fortification, you go through the process of wine spirits addition, WSA for short. But nevertheless, there are various categories of material that qualify for adding to wine spirit. Adding to wine. Wine spirit can be, first of all, neutral spirit distilled at high proof. 190 proof normally is a dividing point between material called brandy and that called spirit. There's no product that if it's distilled at 190 or higher proof that you can label brandy. That's excluded. It now becomes spirit. In reality, it would be called, most of the neutral spirits would be produced from residue material, but that is an eligible material for distilling neutral spirit. Now, if we distill brandy, at some proof which is not exceeds 189, but still is greater than 170, or in other words, between 171 and 189 proof, it is legally classified as neutral brandy. This, of course, is entirely eligible for addition to wine, and so it includes part of the category of wine spirits. Most of the residue material, that is, the pumice, is left after making either white wines or red wines, fortified wines, or even sometimes dry wines as well. The residue can be extracted in some way or another with water, and then distilled. That, strictly speaking, would, if it's in this range here, brandy, if it's let's say distilled at 189 proof from pumice, the technical term would be neutral residue brandy, because the word residue then applies, and that's not eligible for anything except wine spirits. The use as wine spirit. And finally, although this is not normally done, you can use beverage brandy distillates for fortification of wine, as long as the proof has not been reduced below 140. There's one producer, small producer, that chooses to use a beverage brandy distillate for fortification of his port in order to get some flavor contributed by the brandy to his port wine.
Can't go below 140?
There's only one exception that you can go below 140, and that is if you choose to use aged brandy, brandy that's been aged in wood. And then I'm not quite sure what the, I think any aged brandy as it comes out of the barrel is eligible to be used at whatever proof. Maybe I have to check up on that exactly.
I'm confused about this beverage brandy. On the point you're saying it's less than 140 proof.
If you have a beverage brandy distillate, which means it's made out of whole wine and distilled 170 or less, it can be used directly, but it cannot be reduced below 140 proof, or in other words, it can't be distilled below 140 proof. Or you can't take it, if you'd made it 170, you could add water down to 141 if you wanted to. There'd be no point in doing it, but this would still be legal. But if it's below 140, then it's not eligible to be used in winemaking. With that one small exception, which is practically never practiced, of using beverage brandy out of a barrel that would be normally ready to sell as a beverage, that can be used for fortification at less than 140 proof. I'm not quite sure whether the minimum is 80 proof or somewhere around 100. Question?
Yeah, on your neutral brandy, 171 to 188, this can be added to wine, you said, if it's not distilled from lees or pumice?
Oh, it can be added to wine if it's made from pumice.
Even if it's residue?
Any material, in other words, to make it simpler, any material distilled from grape material, whether it's residue, whole wine, or what, or waste wine, this low-quality wine that wants to be disposed of, can be added to grape wine, provided the proof is 140 or more. But if it This reminds me of a slight point here, or a minor point which I might make, and that is that to make fortified wines, or wines to which you have add spirits, the law requires that the spirits be made from the same kind of fruit, as the wine to which is to be added. For example, you cannot make spirits out of waste apricots and peaches to add to grapes in the fall. By the same token, you cannot use grape brandy, which is more readily available, to add to, let's say, fortified apple wine or peach wine. Question?
What's the difference between the beverage brandy under 1A and the beverage brandy distillate under B?
None. That's the same as this. This is really the same thing. This is sort of a little classification according to the usage. And this particular material, although it's beverage brandy distillate, is primarily produced for the purpose of eventually selling a beverage brandy. That material can be used for wine spirits, as wine spirit. That's some slightly overlap then. Yeah?
Can number 3 be made from residue, or would that be made from it's labeled as that?
Well, no, beverage brandy cannot be made from residue, otherwise it's be called residue brandy.
So
I guess the law doesn't preclude you from making residue brandy out of waste material, then aging it in wood and then bottle it, but the label will have to say residue brandy, so no one does that. The law does not preclude you from making, distilling at 180 proof either, and aging in wood and selling it as brandy, but it has to have the word neutral on the label, so no one does that. But if they decide that for some reason that the advantages might override the disadvantage, or what they might presently call stigma of the word neutral, they're perfectly permitted to do so. Well, this is and leads us into a little discussion about distillation itself, and perhaps might attempt at some definition of the word distillation. Most of you are aware of what it means, and we say in general that it's a process by which you cause a liquid to be converted to a vapor by the application of heat energy, and followed by the removal of that heat energy by cooling and condensation, or to produce condensation. And the condensate then represents a product which has affected some separation. Well, now that's not a definition that you would find spelled out exactly in those words anywhere probably, but in fact this is what we do. Distillation is considered a separational process, and the separation is affected by a vaporization step. Usually when we apply the word distillation, we're talking about a separation of volatile components from each other. Although to a certain extent you sort of speak of distillation when you distill off the liquid from a residue so as to leave a non-volatile residue behind. This is not much different than evaporation. In fact, there's no sharp line of demarcation between distillation and evaporation. Generally speaking, when we apply evaporation to the process of vaporizing a solvent which is of no interest to us, primarily water, and we may condense it or we may not, and in order to recover or concentrate the non-volatile solids. So anyway, distillation is essentially a process as we apply it to separate ethyl alcohol from water in the alcohol industries, or partial separation. Of course, we also separate the volatile constituents, which are alcohol and some of the water, from the non-volatile solids, the salts and acid radicals and tannins and residual sugars, or not fermented sugars. But anyway, I wanted to just say a few words about kinds of distillation, classified in a simple fashion according to the process that's used. Later on, we'll have occasion to discuss each of these in turn in some detail. So, first of all, I'd like to make the major classification according to the process into whether it's continuous or steady state versus discontinuous or batch. As I think I indicated yesterday, a continuous distillation or steady state process is one which the process, once set in motion, involves the introduction of a feed material or materials, that may be more than one, into a process at the same rate at which the end products come out, so that there's no depletion or accumulation in the middle. Now you can have a little modification of continuous processes in which you do have either an accumulation or depletion of some component within the process, but in most cases in distilling, we're talking about a completely balanced process. Then we can classify this into one stage or one step of distillation. In other words, if you take a liquid and add heat to it and produce a vapor and condense it to a liquid, we have applied one stage of distillation. And we effect a certain separation, depends on the characteristics of the components. The basis of distillation, to digress just slightly more, is the differences in vapor pressures. If we take ethyl alcohol and water in a mixture, generally speaking, ethyl alcohol has a greater vapor pressure than ethyl alcohol. So when it becomes a vapor, there's a relatively greater concentration of alcohol molecules in the vapor phase than in water. So when we condense it to a liquid, we have an increase in the alcohol content in the distillate. But water still has vapor pressure, and so a certain amount of water comes over. Roughly speaking, if you took 10% alcohol solution, the first distillate that'd come over would be around 5 times as much, maybe about 50% alcohol. As long as it was still 10% in the liquid, the vapor would be around 50%, roughly. We'll go into that more. We have charts which we can show exactly what it is. So, we get a certain concentration in a single stage process. I mean, in a single stage of continuous distillation. In actuality, a single stage continuous distillation is not particularly used, that I know of, in beverage industries for production of alcoholic spirits, but it is a useful process, and it involves what we call flash or equilibrium distillation. We'll talk about that more later, but this is sort of different than the other 3 types in that we don't use it directly in producing alcoholic beverages or distillates. But the process that's most widely used, at least in the United States, for producing alcoholic distillates is the type we might call multi-stage continuous distillation, called continuous rectification, or you know, rectifying distillation. And I'll just go through this chart, and then I'll come back to that. But in effect, we accomplish this by having a column, which we have several stages of vaporization, condensation. In effect, trays or plates in a fractionating column. We call it fractionating column. And so we have a repeated, in effect, a repeated vaporization and condensation, so enrichment at various stages. Several steps. Distilling column may have 10, 20, or up to 100 different stages in it. Depends on what the function is and the purpose. Then we have discontinuous distillation, more commonly called batch process. And strictly discontinuous or batch process involves putting a material into an apparatus. As far as distillation is concerned, applying heat to the material and causing it to vaporize and collect the distillate, but no addition is made to the pot or the boiler until the process is ended. So consequently, in general nature of batch distillation or pot distillation, simple pot distillation, if it's only one stage, is that you have, as a function of time, you have a continuous change in the composition of the liquid in the boiler or the pot, as well as a distillate, naturally. And so you do not get a uniform distillate. In contrast to that, with continuous distillation, we assume we have a constant feed material going in, and so that the composition inside the vessel does not change and the distillate does not change as a function of time. But in batch distillation, it does change during the time of the process.
In the continuous, isn't there a collection of some water? If the alcohol is coming off faster and the water's remaining behind, even though you're feeding in more of the beginning material, aren't you?
No, in a true continuous distillation, whatever water doesn't appear in the product goes out another product, which is the bottom product or the waste, stillage, at the same rate that it enters.
So what comes out is not only the distillate but also the waste.
Oh yeah.
Coming out at the same proportion.
Yeah, I'll draw you a sketch of one in just a minute here, but, to show you the general process, and then in the laboratory today we'll have a look at our little pilot column, which shows you the features of it. So then let's conclude this outline here by saying that, as I've already said, I think if you just carry out a single vaporization, a single step, we call it simple pot distillation, or the technical engineering term is differential distillation. Now, I'm going to go into the reason why it's called that. But this differential term is sort of synonymous with and frequently confused by the students with this term equilibrium distillation for a single-stage continuous distillation. Later on we'll stress the reason for those words. Now, just as we did here, we can have multi-stage, and we accomplish this by having a pot with a rectifying column or a plate column on the top of it or connected to it. So we can effect, even in batch distillation, a significant concentration up to the desired level. Let's say in one step or one process or one operation, if you have a rectifying column attached to the pot, by pot rectification, the necessary concentration. Now let me say that this method and that method and this method are all used in the wine industry, used in the alcohol industries and the wine industries to produce alcoholic beverages. In California, the most commonly used method for producing beverage brandy and wine spirits is continuous fractional distillation. That's another word I didn't put on here, continuous fractional distillation. However, the use of batch processes it has considerable importance in the world and very limited extent in California, but I might point out that by using a simple stage or a single stage or simple pot distillation, you normally do not produce sufficient concentration of alcohol to accomplish the desired end. So it is repeated at least once, sometimes 3 times, or that is repeated a second time, or a total of 3 distillations. But usually 2 successive simple distillations is a process used for producing cognac, for example, France. In fact, it's the process that's we'll talk about more in detail. That's so widely used that it's called the Charente method. Charente being the geographical departments where cognac is located, or méthode charentaise. 2 successive simple distillations are also used in the Highlands of Scotland to make what we call the all malt whiskies of Scotland. Those which contribute most of the flavor to scotches, even though they're sold mostly as blends. This is another subject, but generally speaking, Scotch whiskey, you notice on the label, it says blended Scotch whiskey. Well, that's a blend of the pot still whiskies made in the Highland district of Scotland, where they use only malted barley rather, as the grain, and made in simple pot stills by 2 successive simple distillations. It's blended with material which wouldn't be neutral brandy, which we'd call sort of categorize in this area here of neutral whiskey, distilled in continuous stills around 189 proof, something like that, and then these are blended together. Okay, any questions about this little outline so far? Now I take a few minutes to indicate a few simple features of a continuous distilling column. The apparatus by which we can conduct continuous rectification, fractional distillation, usually consists of a column in which we have a series of trays or plates. Now, these may be of various designs, but the most common is what we call bubble caps. And a bubble cap tray or plate is a device that has, if I draw just a little cross-section of a larger scale here, is a device here which has a series of holes with risers, and then over these holes are caps. called bubble caps. And from the tray above, which I won't sketch, there'll be the liquid overflow coming down. There'll be an overflow liquid running down here. This could be in the stripping section and would be the wine primarily flowing in here. Oh, excuse me, I didn't intend to put a cap over that one because this represents the overflow down to the tray below. So in functioning, we have a vapor produced at the base by steam or heat, and this ascending vapor rises up through here, and by the nature of this tray or plate, a certain level of liquid is trapped here because it hasn't any way of getting out except to overflow at this weir, what we call the weir. The weir can be just the perimeter of the projection of that tube, or it can be some other types of weirs that control the liquid level on the tray. But anyway, the primary function of a tray or a plate is to provide some mechanism by which ascending vapor can interact with, bubble through, or react with a descending liquid stream. And in effect, then, we produce what we consider one stage of vaporization at each tray. In other words, the liquid running down here will give up some of its more volatile component to the ascending vapor, so that the vapor rising from this will be somewhat enriched in the more volatile component, in our case alcohol, and the liquid overflowing here, the liquid stream, will be somewhat deficient in the more volatile component, namely ethyl alcohol in our case. And so this process is repeated from step to step, and eventually we have sufficient concentration of the more volatile component toward the top, and to produce our desired product, and we have sufficient removal of the more volatile component from the material, or let's say the water phase, by the time it reaches the base, to satisfy our requirements or specifications. Now, in reality, the simplest type of a continuous distillation column then consists of two sections. And the sections are divided by the point at which we introduce the feed or the wine. Of course, continuous distillation is used for many things besides wine, so the general engineering term would be feed, or the material that goes in to be separated. But in the case of our brandy industry, the feed material would be the wine, or the wine-like material. Now we speak of the part of the column that is below the feed as the stripping or wine section. And the part above it, above the feed, is spoken of as a concentrating or rectifying section. So, in its simplest form then, we have to have a feed material, we have to have some mechanism of starting the vaporization process, and the simplest way in the case of alcohol water is to introduce direct steam in the base. That's frequently done through a little perforated tube or ring here called a sparger, which the live steam mixes directly with the liquid and therefore produces the necessary vapor and heat. Although this isn't the only way it can be done. It can be done by heat exchanger, so that you do not have direct mixing, in which case we call it a reboiler or a calandria heating. Our little pilot column is equipped for both. And so we have, this produces the ascending vapor, and eventually the liquid that's appearing here in the base goes out as a bottom product. The proper term would be bottom stream. In the case of the alcohol industries, the common term is stillage, or you could say de-alcoholized wine if you'd like, but stillage is an engineering term. And then in its simplest form, we would have the vapor arising from this top plate would pass off to a condenser. The condenser may be various designs, either vertical or horizontal. It usually is tubes encased in a shell, and the vapor is condensed in the vapor space outside the tubes, but I won't go into the details of that. But suffice to say that can be represented by a little rectangle here in which, let's say these lines here represent tubes. Instead of just 2 or 3, there'd probably be maybe 100 in here. And so the vapor is condensed around the tubes. Water goes in here, and water goes out here. That is cooling, condensing water. And the distillate comes out here. And some of it may be taken out. I'll just draw a single line. Some of it may be taken out of the product, controlled by a valve, but a good part of it has to be returned to the top tray of this column as what we call liquid, or as reflux, or liquid overflow, and this would be the distillate. Now that would be the simplest arrangement for continuous distillation, where you have a single feed material going in and you separate into a top product and a bottom product. We call it the top product and the bottom product because the distillate here came from the top of the column and the bottom from the lowest part of the column. In reality, we don't use this exactly anymore. All this used to be the process, but in practice, and I think maybe I might as well re-sketch that in order to make it clearer, we separate the feed material into at least 2 streams of two different products, and sometimes 3. In the case of, and we may use more than 2. We may use more than 1 column to do it, and more than 1 section, more than 2 sections. But let's see, the usual type for brandy production, beverage brandy production, is very similar to that, except that we have the feed going in here, the wine, and we still have the stillage coming out. There's no change here. And we have steam going in here to supply the heat. But now, instead of taking the top product off here as the main product, we'll call this, we take some of this and call it a heads product, a rather small part of it, but the main product will be drawn off as a boiling liquid from one of these trays here. We call this a side stream product. Or side stream. And this might be the main product. In fact, that is. In the case of beverage brandy and other types of brandy distillates, of course, this goes through a cooler in order to cool down this boiling liquid down to acceptable temperature. And again, of course, we have liquid run back here as reflux or overflow. So in other words, then we've separated the feed into not only into the de-alcoholized wine, but into what might be a high alcohol material testing around 190 proof and containing a relatively higher concentration of the low boiling constituents like aldehydes and ethyl acetate and sulfur dioxide if it happened to be present. Into the head stream, the main product coming off here is the side stream. Now, in the case of producing neutral brandy or wine spirits, this side stream product might be a little higher up here, and we probably have more plates, but we might also draw off a stream here which we'd separate fusel oil or the higher molecular weight alcohols. And we don't have time to go in that today, but it's a case where, well, it's almost necessary if you're producing neutral spirits that are in reality are neutral to take out oil stream or a fusel oil stream, because they the higher alcohols, like isofamyl alcohol, it's almost essentially impossible for them to distill in the range of 190 or 192 proof, so they accumulate in the middle of the column, and if they're not taken out, they'll become such a concentration in the middle of the column, they'll interfere with the operation. And so they're removed, not only for that purpose, but in order to ensure that they're not in the product. In the case of beverage brandy distillation, if it's truly distilled at 170 or less, it is impossible, or rather difficult, let's say, to make it. Well, it's impossible to do it in a simple separation, as we can do it in high proof distillation, to remove the higher alcohols. There are some techniques I'll later talk about how it can be done, however, to minimize or lower fusel oils in the distillate for beverage brandy purposes. Well, with that sort of sketchy outline of what we're about, we'll conclude this talk and this period, and then I'll just say a word about what we're going to do in the laboratory, but I'll explain it when we get there. We have two things that we're going to do in the laboratory, and one is familiarize you a little bit with the technique of gauging. Gauging meaning the determination of proof and the quantity of spirits. That's simply all there is to it. And the primary way to determine gauging is, as far as proof is concerned, is with a hydrometer and a thermometer. And we utilize tables in this gauging manual to correct to a constant temperature or the true value of proof. And then we have to measure the amount either by volume or by weight. And tables in this convert weights or volumes, if you have, to whatever desired units you want, and generally proof gallons. So we're going to have a little practice in that. I have a little problem set to work out here in the laboratory to illustrate the various tables. There's 7 different tables in this book of some 500 and some pages, and most of it is tables. Table 2, for example, occupies, I think, something like 400 pages in the manual. And then secondly, we will take maybe half of each lab section and take a little tour to show you the pilot facilities that we have. I can illustrate continuous distillation, single stage batch distillation, multi-stage distillation. We used to have a flash distilling apparatus, but can't think where one is now. Been torn down. But I can also show you a vacuum distilling column, which is in effect continuous multi-stage distillation, but instead of having trays, we have a pack column, and we use it for a specialized purpose, that is low temperature distillation. But that can make it not fit this particular category of classification. Okay, that'll be all this morning.